This talk is called Isolation Without Containers. If you're expecting this to be a talk about containers, I am going to greatly disappoint you. You might be in the wrong place. It's okay. This talk is much more about the concept of isolation, and then we also get into some like cool compiler stuff. So that's neat. Hi, I work at Fastly, which is a content delivery network, or a more of like an edge computing network at this point, to be honest, with the stuff that we're doing lately. I'm the CTO there, and you can follow me on the internet here. You can argue with me. I enjoy being yelled at. It's fine. Great. So this talk, I say that it's about isolation and not really about containers. What this is really about, actually, is about multi-tenancy. It's only about isolation because what we need to provide like a working environment for a multi-tenant thing is isolation. You need isolation between customers and services and all these different things, right? And so the obvious first question here is like, what is isolation? Like, what do I mean when I say that? Because there's a bunch of different ways that we talk about something like isolation. One of those is like resource isolation. You might hear this in with regards to like containers, actually. There's process isolation, which is literally just the process model. There's fault isolation, there's software fault isolation as well. And there's lots of different ways to do this, right? And so I'm just going to be talking about one particular kind after we go through like the concept, right? So the way that I look at the concept of isolation is that it's really about being able to run some code without it affecting other running code in unexpected ways, which is a vague statement, but it's fine. So part of that is resource isolation, and we'll talk about that more in a little bit and why it's not just about efficient use of resources, but what I actually enjoy, like there's a concept called FDIR. It's not, does anyone actually, has anyone heard of FDIR before? No one. Yes, great. So this is the, FDIR stands for Fault Detection, Isolation, and Recovery. So it's a concept from control engineering. It's usually referring to monitoring things like thermal signatures and vibrations and oscillations and so on. So it doesn't apply directly, but more in a metaphorical way to what we're talking about. I like it because it separates out the three stages: detection, isolation, and recovery. Detection implies being able to tell when a fault has actually occurred, which is less trivial than it might seem at first. Isolation in our world means being able to prove that when a fault does occur, that its like blast radius is known and limited, right? And then recovery, for us anyway, means being able to ensure that the execution can be restarted, and that the system continues with the rest of the tenants being like oblivious that a problem has actually even occurred at all, right? So in a program, in a computer program, I think, and I don't have like, you know, papers and such to back this up, but in my mind, the way that I think about this is that it kind of comes down to two things. One is control flow, and the other one is memory safety. When I say control flow, what I'm talking about here is the analysis of the set of possible paths that an execution of a program can take, right? When I say data flow, what I mean is the analysis of locations that a program can be storing and retrieving data from in memory. My conjecture here is that if you can work out these two things, you've essentially solved most isolation problems. Interesting side note here is that, you know, as we'll see later, you can actually reduce these down to one thing if you really think about it hard enough, which is memory safety, but it's fine. Let's talk about it. Okay, so what we're really talking about here is, okay, so let's say we're executing a function, right? And it's really about being able to prove that that function can write to one particular area and can't write to another area, and likewise, it can call another function or can take a particular path, and proving also that it can't take certain paths. When you examine what guarantees, if any, you have for control flow integrity and memory safety, what you get out is a fault domain, right? A fault domain is the answer to the question, like, if this program just like fucking blew up, what would happen? Like, which things would also blow up along with it, right? What could possibly be touched? Fault isolation is really about reducing the set of possible faults to something that is knowable and recoverable. For instance, if certain code should not be able to be executed, fault isolation is about being able to prove that it's either not possible, or that if it is possible, then when it occurs, we can catch it and prevent it from actually like falling through before any harm is done, right? Okay, so The problem that we set out to solve at Fastly for this, that my team at Fastly set out to solve here, was an interesting one. Because what we wanted to do was isolate every individual request that flows through our network, right? And so we're talking about like 7 million requests per second at this point. We want to isolate each individual one of them so that like the code that is being run along with them, if that blows up, like we want to just have that one request die and nothing else be affected. So each of our servers is doing like tens of thousands of requests per second per server, and like the lifetime of these requests is typically like well under 5 milliseconds. So this becomes difficult pretty quickly. Like if you've tried to spin up processes or containers in that kind of speed, like that's really pushing it. So yeah, the obvious question is how could you possibly do this? So one of the first things, like, let's talk about like how processes work, right? Like what actually is a process? So that's what a process is. That is the task struct from the Linux kernel. So the question of what is a process turns out to be fairly complicated. But we can actually like boil it down to a few things. So what we have here is you have memory and you have the metadata in the kernel that is associated with a process, right? Like that task struct that we were just looking at, that's the metadata. That's the data that is associated with a process that lives on the kernel side of the memory boundary, right? From a process's perspective, all it actually has is memory. Like that's all a process actually is. That simple little thing is actually like the crux of process-based isolation. The memory region is by default anyway, like the fault domain of a process. That's it, that's all it is. Yeah, so like the biggest component of process-based isolation is this idea of virtual memory. Virtual memory uses like the hardware MMU and the kernel's VMA systems to give each process like an illusion of having its own memory space. Like there's nothing else on the computer. There's nothing else there that it can touch, unless, of course, you explicitly share things. Yeah, so another key part of this is something that probably seems entirely obvious, but the fact that code and data live in the same space. Like we kind of take this for granted, but like the fact that that is the case has interesting implications, right? So process-based isolation works because if the only thing a process has access to is its own memory, and that is also where the code lives, then we don't really need to worry about control flow. We don't really have to think about it. Basically, like the inside of a process can be complete chaos, and it's fine. So it's interesting because it really strongly ties us to the safety properties of the virtual memory, though. And so like when the Spectre attacks came out earlier this year, I think this is one of the reasons why it was like such an enormous deal, right? Because everything that we rely on is around virtual memory. And so if you have an attack that breaks the virtual memory, like abstraction, like everything is going to hell. So yeah, I think that's just a side note as to why I think Spectre was like such an important thing. Okay, the other thing that processes have access to is an interface with the kernel, which is syscalls, right? Calls that affect the process itself or like allow it to communicate with other processes or other computers. So it's via syscalls that we give processes the ability to interact with other things on the system and with other processes, right? So this is an interesting thing because if I say, all right, I want to mmap some piece of, like some file in a shared way, and then I try to mmap it again from another place, well, okay, now we're actually sharing information, right? And so now the fault domain of each of these individual processes now includes each other. So you can pretty easily start to like break this like virtual memory like isolation model, right? And it turns out that containers actually follow like almost the exact same ideas, but they apply like further resource isolation things to it. So like PID namespaces and syscalls and so on, right? But the basic idea is really the same. So let's talk about something entirely different. Let's talk about dynamic libraries and dynamic linking. So this is literally what I mean. So if you're in a process and you DL open something into it, like what does that actually do, right? Dynamic libraries provide us a way to like load new code into an existing process. from outside, right? We can DL open a shared object, locate a function inside of it, and like execute it directly within the address space of like one of these processes, right? And so you might think about like loading dynamic libraries in a similar way to how we were talking about processes, right? So you have the symbols inside the process, and you have the symbols that you just loaded into it. And so, of course, we start to develop like almost like in a weird way like a syscall interface, right? Where you have some undefined symbol in a dynamic library, which the process then provides. So you have like this interface. Likewise, like the process can use DLSym to grab a specific function out of a library, right? The issue here is that it's not really like processes at all, which might be obvious to everyone here. Those interfaces exist and you can use them, but the problem is that those interfaces are actually just a convenience, right? Like, they're actually all living together with no boundaries at all. So if you load multiple libraries, there's nothing that stops it from just, reaching into like one piece of memory somewhere, or reaching back and forth here, or, just jumping all over the place. It's fucking chaos is what it is, right? So like, this doesn't actually provide us any of the isolation that we would be hoping for. So why do people use this then? Even inside of Fastly right now, like the way that we handle like loading customers' configurations is actually by compiling them into a shared object and loading it into our server while it's running. And the reason that works, of course, is that like we provide like semantic safety guarantees on the language itself, right? But at this layer of things, there is like essentially like no safety at all. So why do people do it this way? And the answer like really just comes down to overhead. So if I were to have two different ways of doing like communication between processes, between pieces of code, if you were actually separating them by process, then you're going to be going through the kernel for each individual thing, which takes a long time if you're talking about tens of thousands of requests per second. Meanwhile, a library can just be like, I just want to call that thing over there, like zero interface with the kernel at all, right? So this is kind of why people do that. But the issue, of course, is safety, right? The problem here is like we have traditional isolation, which is like often too heavyweight for these small tenants that have like very strict latency guarantees, right? So doing it in the traditional way doesn't necessarily work. So what are we to do? One way to address this is to provide isolation at a higher level, which is what I was kind of saying that we do with the programming language that people often use to configure our CDN, right? We provide semantic safety at the language level, right? So you can do it via higher level isolation, but what if we wanted to do it in a more general way? What if we wanted to do it such that like you didn't have to write in my language, you could instead bring whatever language you want as long as we can compile it in some way? And this is where WebAssembly comes into it. So, one of the interesting things about, there's several really interesting things about WebAssembly, but one that is particularly interesting to me is this concept of like linear memory, right? So WebAssembly has, this is, by the way, like a complete WebAssembly module here. Like we have our code there in the middle, like the function main. We're importing a puts function as well. And then down at the very bottom, we're saying, okay, I'm going to use one page of memory, and here's some data that I want to exist in that when I start up, right? Oh yeah, I said these things already. Okay, great. So one of the key differences between like a WebAssembly instance and a regular process is that, so you remember like the whole thing with virtual memory and the fact that you have the code inside of it. Well, WebAssembly doesn't do that. It does it entirely differently. Like we actually separate out the code from the memory when it comes to a WebAssembly instance. So we have the code that doesn't even have access to itself. All it has access to is the linear memory and an interface with the outside world. So the goal of this is to constrain the fault domain. So if we have many of these that are running in a single process and we can somehow guarantee that they are going to stick inside of their like little region of memory, then we can make that little region of memory be the entire fault domain for one of these processes, one of these instances rather. We're going to skip this part. Sorry, I added more things and forgot to take that out. Okay, so given that, you can only call functions which the host environment has allowed you to via that import interface, and you have no way of referring to locations within your own code, right, because it's separate from the memory. And by extension, you have no way of doing things like computed go-tos, which could send you wherever you want. Control flow is something that like WebAssembly actually provides. And if we can use WebAssembly in a system like this, it would provide control flow integrity. Likewise, we also get memory safety from WebAssembly. So linear memory inside of WebAssembly is based on 32-bit pointers. So essentially, like the maximum amount of memory that a WebAssembly instance can have is 4 gigabytes, and we just like, so you refer to that with these 32-bit pointers instead of 64-bit. And the reason for that is that it makes balance checking a lot easier, which we'll go into. Right, so in other words, with WebAssembly, you can actually reduce the set of data and memory-related faults to one that is knowable and non-fatal for a process. Cool. Okay, great. So if we can compile our code to WebAssembly, then we can actually get the safety that we need. And it turns out that like Clang, Go, Rust, and others all have WebAssembly backends now. And this to me is actually one of the most exciting things about something like WebAssembly. It's the fact that it is, as far as I know, the first time that we have as a community like an intermediate representation that most people have, like a lot of different languages have actually agreed upon, and one that provides safety guarantees. Right, like that's something that we've never actually had before, which is why this is very exciting to me. So great, we can take our code, we can compile it to WebAssembly. As long as you are writing in a language that you can compile to WebAssembly, great, we can bring that along, we can use that. But of course, that's only half the story. We still have to compile the WebAssembly to native code. So how do we do that, given the fact that the only existing WebAssembly-like compilers are built into browsers and are for JITs as opposed to for ahead-of-time compilation like we care about here. And of course, the native code has to be fast, because again, we're doing tens of thousands of requests per second per server. So what we've been working on, and I will say in advance here that this is not yet open source, or at least not completely open source, but will be very soon. So again, follow me. I will undoubtedly tweet things about it. What we've been working on is a compiler that takes WebAssembly and turns it into native object code, as well as a runtime that lets you run the thing. So at its core, the runtime actually looks a lot like this thing that we just talked about how incredibly unsafe it was. But when you have a runtime that provides certain guarantees and you have a compiler that like works with that runtime to provide the other set of guarantees, you can actually make this entirely safe. The interesting thing about this is that like the objects that we output actually look exactly like regular like ELF libraries, right? So you're taking WebAssembly code that was meant to run in a browser and turning it into an actual just normal shared object, just like any other shared object on your system. But there are a few differences. There are some like interesting bits here. And so this is where I'm going to eventually get into some assembly. I hope that everyone here is prepared for some x86 64. But two of the bigger differences between the libraries that we output and like a normal library involve the calling convention and something called trap tables. So I'm going to talk about both of those. So let's talk about calling convention. There's actually only one minor difference between like calling one of our WebAssembly libraries versus calling a function in any other normal way. Right, so the primary difference is this, is that when you call a WebAssembly function, an ahead-of-time compiled WebAssembly function with this, RDI is set to something called the VM context. So what this does is it allows you to, this is the thing that actually causes the sandboxing to work, right? So all memory addressing happens via this virtual machine context. So what that looks like is this. Essentially what we have here is this is the fault domain for one of our instances. So we have the metadata associated with it and the linear memory, much in the same way as processes work, right? And that VM context points to there, exactly there. And so what that means is that as execution is progressing, you can take that pointer and go upward and find things like tables and globals and other metadata that's associated with this instance, or you can go down and get to the memory. And so that is like the actual like one piece of information you need in order to sandbox this code at runtime anyway. So what that also means, of course, is that memory is all vectored, memory addressing is all vectored through that particular VM context. Remember, because the memory is downward from that context pointer, that means that any time that we would want to access a particular address, we do it via this context, right? So that being the context. Okay, I'm going to talk about the other part that actually makes this work in a safe way, and that's something called trap tables. So imagine that we have a WebAssembly operation that looks something like this. And what this essentially is saying is just, okay, I want to load an i32, an 32-bit integer from memory, and I want to get that from the local variable number 0. Right? So the address of this is in local variable number 0. What this ends up looking like is that machine code, 8B07, which becomes this. Which is essentially, again, we are vectoring through the VM context and putting it in RAX. However, what this also does is we need to be able to bounds check this, right? And so that's the other key part of this that makes running this code safe, is that all of the memory operations that we do are bounds checked. But of course, bounds checking is slow, right? But we will get into that in a little bit. The interesting thing here is that when we're compiling this, we know that this is something that could trap. We know that this is something that could go out of bounds and could blow up, right? Because we don't know what address it's actually going to be looking for initially. So what we do is we say, okay, this is a site that could trap. This is a particular operation that is capable of trapping. So we call it a trap site. And what you do is we essentially, inside the generated library, for each different function, we have a trap table. And what it does is it says, okay, at this exact offset within here, if it blows up, here's exactly what it was, right? So in this case, let's say it was 8 bytes into a particular function that you're making a memory reference. So we know that that could provide a heap out of bounds trap. What this also tells us is that if we blow up somewhere else, that is fatal. Right? This gives us a way of knowing whether or not what we have provided, like what we have done is whether or not a particular trap, a particular like seg fault, for instance, is actually safe. Okay. Right, so bounds checking. Bounds checking is like, so this is like a key part of how WebAssembly works. The problem with it is that traditionally doing bounds checking has been incredibly expensive. Right? There's a reason that many languages don't have it built in. That's actually like entirely speed related, right? I've read several papers recently about this, and some of them would see between like 2 and 10x slowdowns if you actually put like strict bounds checking into C code, for instance. So like it's kind of gnarly. However, WebAssembly actually does some things to make this quite a bit better. So if we go back to like the virtual memory abstraction from before, one of the things that makes virtual memory like kind of difficult to do bounds checking with is that virtual memory has holes in it. You can map particular parts of your virtual memory space and leave others completely like unmapped, which means that if I want to do something like this, I want to write a bunch of data right across the middle of my memory region. Bounds checking that gets really complicated. So if you look at this particular one, I can't just look at the front of it or the beginning of it or the end of it. Right? Because the beginning and the end are both actually totally valid places in memory. There's just multiple places in the middle that are holes. Right? So bounds checking memory operations like this gets really complicated. Yeah. So what's different about WebAssembly and like the linear memory model for this is that linear memory doesn't have holes in it, and it grows in exactly one direction. It grows up. Right? So what this means is that if there are no holes and it's only growing in one direction, and we want to write into it, the only thing I need to bounds check is the end of it. Right? Because everything, if the end is in, everything else also exists. So that's like a pretty powerful like mechanism there. But we can actually still do better than that. So one of the things that my team and like the other folks working on this compiler have been working on is this concept of bounds check elision. Are there folks in the audience who are familiar with that concept? Some of you? Good. Okay. Right, so we can still do better than actually having to do all of these bounds checks. So imagine that we have some code like this. It's just, I have an array, I'm going to reach 17 elements into it, and I'm going to stick a 64-bit value there. All right, let's walk through how this would work. In a naive setup, the code might expand to something like this, right? So this is the WebAssembly code for this. So we get the local that is my array. We say that, how did this work? Yes. Oh, right, we're putting 0 into it, and we're using an offset of 136, which is 8 bytes, 64 bits times 17. Great. So if what we had was a linear memory model, like if our implementation of that was just, okay, I have several pages of space available, and I'm going to just, that's all there is to it. Like this, I have this much space, and that's all I know. Then what we would have to do would look something like this. And so what is happening here is that we actually have to do multiple bounds checks, despite the fact that I just said that you wouldn't necessarily have to do that. So essentially what happens here is we need to first bounds check the base pointer, so that being the myArray pointer, and then if that fails, we throw what's called a UD2. So this is an explicit bounds check in which if it fails, we throw a sig-ill, right? And so this sig-ill, this UD2 would show up in our trap table, and so we would know, okay, the bounds check for this failed, everything is cool, everything is safe. Then likewise, we need to check the offset plus the size as well. So this is kind of a two-step bounds checking thing going on here. This is kind of the naive way of implementing a WebAssembly store instruction, right? And so finally, like the actual instruction is way down there, way down at the bottom. Cool. So if we were to, however, instead of just saying, okay, I have my linear memory, and that's all I have, it's just linear memory, if we were instead to say, okay, let's put a guard page at the end of it. Let's put a 4 kilobyte guard page at the end. So what a guard page actually is just literally unmapped space. But it's unmapped space that we know exactly where it is and how large it is. What does that do for us? Okay, so going back, what this lets us do is something kind of neat. It lets us just check the base pointer. Right? So if we know for certain that there is a 4 kilobyte guard page at the end of our linear memory and that there will always be one there, it means that as long as the offset that we were going off of from the base pointer is within 4K, we don't need to look at it, right? Because what we know will happen is if we access something that is within that 4 kilobyte region, we will get a seg fault, and we can recover from that seg fault because, again, we know that it's safe, so it's okay. So yeah, we don't have to check the offset at all. Instead, we just check the base pointer. So what that actually gets us is the fact that let's say we had several instructions in a row that look like this, right? Effectively, all we would actually need to do is check that base pointer once, because we would know that as soon as that base pointer is inside the memory, and as long as any of the offsets are not greater than 4 kilobytes, we'll be fine. Cool. So that's like one form of bounds checking elision. Let's go one step further though. What if we, instead of having a 4 kilobyte guard region, we had a 4 gigabyte guard region, which might seem crazy, but it turns out that computers have a lot of virtual memory space. So you could actually fit, I believe it's roughly 32,768 of these into a single process, even having like guard regions that large. So what would that get us? Well, okay, we have this line again, and that's what it would compile to. Right? So given the fact that WebAssembly only has 32-bit pointers, we can say for certain that if something is we have memory region that is 32 bits wide, then we know that it can't possibly address anything that is beyond that. And so we don't need to bounds check it at all. So this is like one of the ways that we're using in order to like take WebAssembly code and make it like really fast, which is pretty cool. Okay, enough assembly, I guess. I'll be done. So how are we doing this at the moment? Well, much of the work of this is actually being done in a project called CraneLift. And so CraneLift is a project that was started by Mozilla last year with some like really great compiler people working on it. It's supposed to be one of the newer like JIT engines that are coming out. We're working with them on it because we want to use this for our ahead of time compilation engine. You can kind of think of CraneLift as like a smaller, lower level version of LLVM with safety guarantees built into it. Interestingly, like someone actually tried to do this with LLVM a number of years ago. It was called Pinnacle, if anyone remembers that thing. So this is a portable, portable NACL with something that was built into Chrome. And so they were essentially had a fork of LLVM in which they had guaranteed that all of the memory operations, all of the operations in there were actually safe. It turns out that maintaining that is a fucking nightmare. So that's crane lift. And so, as mentioned before, the project that we are working on, which wraps crane lift and makes it actually runnable, like, because crane lift is essentially just putting out like raw native code, and so it requires quite a bit of tool chain to make all of this work. And so we'll be releasing this at some point in the near future. But great. So to review, isolation, incredibly important for the way that we do programming today, right? Especially when it comes to multi-tenancy, or even just like the reliability of systems that you actually do trust. Isolation is like critical, right? WebAssembly is pretty awesome. So the reason, again, why like WebAssembly is super exciting for me, and I think for a lot of people, is not just the fact that, cool, we have like a new language in the browser, but rather, again, that it's a widely agreed upon intermediate representation that many different languages can use. And that's super exciting to me. But like really one of the main points of this talk was actually just, I had spent a lot of time thinking about like a mental model for isolation. Like the whole thing where, okay, it's not just about memory, it's actually about like control flow and so on. And that like we can actually think about a lot of these things in abstracts. So that was the point I was mainly trying to get across today. But thank you.